Junction, what's your oh wait. Um yeah. All right. So what I want to kind of do is talk about, in sort of an abstract sense, what functions are, and then we'll actually kind of sort of program some stuff. So let's sort of step back a moment and think about in math class, what do functions look like, right? So what's sort of the idea? Huh? Yeah, some sort of input, you get an output. We write the formula down, f of whatever equals some formula or something. Okay, but the way that we kind of teach this um, in grade, well, maybe not grade school, but certainly in K through 12 education, right, is that it's a thing, it's a magic box, you stick in a number, some other number pops out, okay, and there's probably some sort of formula for it. So for example, I'm just going to make something up. You could do something like just squaring the thing, right? I mean, whatever like operation you're doing doesn't have to be particularly exotic, but point being, numbers go in, numbers come out. Now, I'd like to maybe think more abstractly about this, and rather than thinking of numbers coming into functions, okay, any object, any mathematical object can be the thing that goes into a function and the thing that comes out of the function. Now, oftentimes those objects are things that have numeric properties. Okay, so for example, um, you could have like a function that takes in a pair of numbers and does something with them. Well, that's still kind of numerically based, but the object that's coming in is slightly more abstract um, than just a single number. Okay, question? You could, right? So it doesn't even have to be necessarily a mathematical object in the sense that like mathematicians care about it, right? But you could have, yes, so you could have like, oh, now Thomas, you've really done it. Um, well, okay, let's try since I'm kind of making it insecty. Okay, you have to test my art skills at 8 in the morning. There's a reason I'm a mathematician, gentlemen, and not an artist. Yeah, so anything can be the input and anything can be the output of whatever function you designate. Now, like I said, often the kinds of objects that we'll be working with are things that are sort of built out of numbers, but again, they don't have to be. So, for example, I could have something like this that counts the number of characters, okay? Or I could say something like, oops, I could have a function that I give it a piece of text and I give it a letter and it counts how many times that letter appears in that piece of text. Reasonable kind of thing to maybe want to do. Yeah, so I can have sort of any kind of objects coming in, and then I can return a single object, which often is a number, but it doesn't have to be. Yeah, or not, right? Which uh, right. So really, let me take this example and peel it back a little bit more. Is if we were to actually write this function, and I actually had my other class do precisely this. Um, what am I going to actually look at in terms of counting? Yeah.
Um, the number of H, the number of ASCII encodings matching the thing you're looking
Right.
at.
So really, if I pass a string of text, which is to say a bunch of letters in a row or symbols in a row, those things are going to actually be represented as numbers, right, in the computer. And so what I'm actually going to be looking at is the ASCII encoding for each number and not, or sorry, for each letter, and not really the letter itself. Okay, so that kind of means, right, that in terms of implementing all of this on a computer, right, we're really just still doing number-based things. It's just that we've abstracted in a way to say that certain number-based things are going to represent letters or um, uh, emojis or whatever. Okay. Um, Now, I will also make add one thing to this, which is that a function doesn't actually have to take anything in.
Like in the terminal, when you choose to do Python edits, you can use the quit function, which quits Python.
Right. So, for example, we've used that, like Python's quit or exit, right? Those things. Now, typically we denote that the function does not accept any inputs by putting a set of parentheses where you would put the inputs and just not having anything inside of it. Um, Now, in math class, that may seem kind of like a silly thing to do, where you don't have any input. And in most, think of your calculus or whatever, there's no reason to necessarily have one of these functions. And so you can think of these as being basically just shorthand for a bunch of other procedures. Okay. Um, and functions don't actually have to return anything either, right? So you don't necessarily have to have input or output in a function in a computery kind of way. Now, like I said, in math, it's probably not particularly useful to do that, okay? But functions in math tend to be single line formulas, nothing really horrible and crazy. It's in computing, of course, where they get more exotic. Okay. Um, and it's not to say that you can't do functions that have no input and no output in math class. It's just that their utility is not as apparent in sort of practical mathematics, where you would sort of consider those if you were being more, um, well, doing one of two things: either doing logic, okay, type stuff, or doing things that are basically like the mathematical analysis of a computer, which is kind of what, of course, we're here to do. Okay, so let's actually write some things. And let me go here to our Python. So let me make a new function or program, and I'll call this functions 1.py. Oops. Oh, go away. Okay, so let me just start with defining a function that's, maybe something like what we would have started with. Like in math class, f of x equals x squared. Okay, perfectly reasonable function. So the way I'm going to do that is I'm going to say def, and I've got to give the function a name. So let me just call it square, if I could type. And it takes in some number, and I need to give that number or that object some sort of name. X, and doesn't really matter, just pick something. Um, and then what is this function going to do? Square the number. Okay, so I'll say answer equals n times n. Oh, I'm sorry, if you guys see me putting semicolons and then erasing them, it's because in my other class I'm teaching them C, where you do have to terminate each line with a semicolon, and it's just muscle memory at this point. But you don't have to in Python. Okay, so this function does nothing particularly special. It just squares a number. Okay, and then I could do something like take an input, and then I could do something like print square of number, something like so. Okay, so we want to do, okay, so right now the keyboard, like it's waiting for me to type a number. I'll type a number and, oh, right. Okay, hang on one second. Let me drive. Um, oh, can't do that either. Okay, why isn't it not converting to an end? Yes.
You don't have an output from square.
Oh, duh. That would help. There we go. Okay. Right. So in math we would write this something like um, f of n equals n times n. Okay. So what I need to specify when I'm writing this in, well, Python or whatever language is what are the variables or objects that are coming in, and then what am I going to return? Okay, so in this case, I'm going to return the object ans, which is a number, and it happens to be the square of the input number. Okay, and then so in Python, you define a function by saying def, because I'm defining something, name of the function, and then in parentheses, a list of the things that are going to come into this function. In our case, we only have one, just a single number. Um, and then your function can do whatever it needs to do. And then when it's finished and you have an answer that you're ready to pass back, you have to say, well, what thing am I returning? I'm returning, in this case, the thing called ans, which is just some object. Okay. Um, so, uh, okay, then in terms of how to use this, so think of these three lines as defining an object, a function, okay? But they don't actually do anything unless you call the function. And I did that here, okay? So the function sort of exists as a thing, but it only actually does some computation if you give it an actual number to compute, right? So in this case, what I did is I just said, all right, let me get a number from the user doing an input, okay, so typing something in the terminal. And then line 8, I have to do that because when you ask the user to type in something, it takes Python anyway, takes this data in as a string, which means that it is a sequence of symbols encoded in ASCII, right? So, for example, I typed in the number 5. Okay, what is 5 encoded in ASCII? Well, let's just look it up real quick. 6.5 hex? No, 3.5 hex. Okay, so it takes in the thing in ASCII, And if I want to process it as if it's a number, then I have to do a conversion from a string to a number. There's a function that does that in Python. It's called int. It takes a string that is made up of digits and then converts it into the equivalent actual number. That's just a specific thing to Python. C, there are several different input routines, and one of them lets you specify what kind of input you want, and then you can process it accordingly. Okay, so good. So I just accept some sort of input and print the square of that number. Nothing particularly fancy. Yeah, and then in this case, how does the user know to type something? They don't. So could I just tell them to? And then there we go. Okay, yeah.
Can't you who puts that as an input to the input function?
Oh, yes, actually you can. So you can do, oops, I'm so used to C. You can actually give that string to the input function, but you see it doesn't terminate the line, and it looks bad because I need to put a colon and a space there so that it just looks better. So, so yes, you can actually give a string to the input function and have it, it will print that. In fact, that brings up a really interesting point, which is in math, a function, can you think of a function that takes in either one or two values? You can think of plenty of examples that take in exactly one, and you can come up with plenty of examples that take in exactly two. But can you think of one, a single function that can take in either one or two things that you've used in math? Well, maybe think about that later. I can't think of one. Okay. Um, so, yeah. Um, but in computing, you can actually get away with this where you'll notice the first time I used the input, I didn't have any input. Well, that's really silly. Okay. Um, let me back up a second. I've got a function which is called input, right? And this function accepts user input typed into the terminal. Well, the stuff inside the parentheses that go with it is the input to that function, right? So I'm using input here in two different ways. When I first had the input function, what did I have? I just had rounded parentheses. There was nothing going into it. But now I do have something going into it, right? So computing functions don't even have to always take in the same amount of things, which is kind of funny. Um, yeah. Um, okay. Anyway, that's true. Okay. So Thomas's point was that yes, you could do that. Let me put it back the way I had it, just to illustrate that. Um, and of course, here the function is essentially the same, except that the print function terminates the line, just basically hits enter, whereas the input thing doesn't, and it doesn't really matter, but um, yeah. Okay, so nothing particularly exciting. It takes in a number, it spits out another number. Yay. Now, let's think about other functions that we could write here. So what's something like this? What would I want to return here? Something like that? Okay, now what's sort of the particular potential problem that I might have? Okay, first off, what is the square root function in Python? I don't remember. It's SQRT, but I think I need to include something. Oh, yes, okay. I have to import. Oops. Where am I here? Okay, so I just have to import basically a math routine in order to get the square root in there. Not a huge deal. Okay, so let me just change instead of square. Let me do my function called square root. Okay, and yay, it computes the square root of the number. But what issues might I have with this function? Yeah, I heard it. Yeah, what happens if I try and put in a negative number, right? So if I do so, okay, it throws an error. Yeah, exactly. Okay. So in this case, the function square root, SQRT, that's built into Python has a piece of code in it that's checking whether or not you actually can do this operation. And why can't we, in the particular input case that I chose, because I can't take the square root of a negative. Or maybe better put, I can't take the square root of a negative number and get a real number as an output, right? Because we could do the whole like imaginary number thing from uh, school, right? Okay, so under what conditions am I permitted to actually compute this? What has to be true about the input number? It can't be negative, okay, which means it has to be bigger than or equal to zero. Square root of zero is perfectly valid, right? It's zero, okay? But square roots of negatives are verboten. So in our case, like the function sqrt already has this built in, so we don't technically need to do it, but let's go ahead and do it anyway. So what would I want to do then to have some sort of check for whether or not this thing, uh, the number is positive or not, or sorry, non-negative.
Um, if n is less than 0,
Okay, we can do it either way here. I can do if n is less than zero. What do I want to do if the number is negative?
return, don't do that, please.
I could. Let me. I'm going to in this case print something instead of returning. Um, okay, let's find out. Let me print this first, and then we'll do it. Oh, and I need a quote, close quote there. Okay, and then else I can do this. Okay, so we'll actually get an error as it'll turn out. Okay, if I put in a positive number, nothing changed. But if I put in a negative number, you can't take the square root of a negative, and then it prints none. Okay, because what got returned by this function? Nothing. Because in this if case, where's have I done a return? No, I've never actually returned anything. And so Python is like, okay, you can't not return something, so how about you just return nothing, right? Um, okay, and so what could I have done? I could have, well, let me just say, oh, I can't put a quote parentheses there. I want to do it this. Okay, fine. And it does that. Okay. Now I'd like to claim that what I just did was kind of bad. Okay. Um, and the reason is, and this is something that Python lets you get away with that other languages don't. And one reason why Python is sort of nice for beginners, but also why one reason that Python is maybe dangerous because it allows you to get away with habits that are bad later. Um, if the number is positive, what am I returning? The square root of it. But what is that I'm returning? A number, right? Whereas if I give it a negative, what am I returning? A string of text. I'm returning different types of objects in different situations. That makes like many parts of my soul just ache. Okay, because you can't do that in other languages. It's bad. Okay. Okay, so I claim that this is maybe sloppy programming to do something like this. For sake of demonstrating what a function is, it's not the end of the world. Um, okay, but it's bad habit to do something like that. And in fact, I would even argue that what I've done is still technically bad because what kind of number is 5? It's an integer, but what kind of number is 2 point blah blah blah? It's a floating point number, right? And I've kind of played fast and loose with these is that they're just numbers, right? But really, are they the same kind of number? No, because like in math, uh, when we talk about numbers, 5 and 2.23, they're just numbers, right? They're real numbers, who cares? But in computing, we have to be much more careful because how are these things encoded? How is 5 encoded versus how is 2 point whatever encoded, right? How is an integer encoded? Yeah, you just do it. Okay. And then how is a float encoded? Well, that whole bit with the sign, the exponent, the mantissa, all of that jazz. Yeah, and you guys discovered just how fun it is. Yeah. Okay. Now, in this case, it's using obviously more bits than we did when we were doing. Yeah. So this happens to be a 64-bit floating point. Okay, whatever. But point being, it's still encoded using sign, exponent, mantissa, and all of that jazz. Um, and that's a different kind of encoding than just as a straight integer. So okay, so yeah, I'd argue that maybe I'm being slightly sloppy here with um, oops, wrong thing. I'm being slightly sloppy here, but it's okay um, because well, I'm just doing a quick demo. Okay, so so I guess the point here, or a point, is that the function doesn't have to be a simple like uh, mathematical type function in the sense that like for example the squaring, right, that's the kind of function that you would totally encounter in math classes and no big deal, f of x equals x squared, right? But it doesn't have to be that simple in the sense that you can have conditional expressions inside. You could even have loops inside. Okay. Why might we want to have that sort of thing? Well, for example, let's take the character counter, right? Where I give the function two things. I give it a string and I give it a character, and I ask it to count through how many uh, of a given character appear in a given piece of text. Well, I'm going to have a loop to do that, where I'm going to look at the first letter and see if it matches or not. And if it does, add to a counter. And then I'll move on to the second letter and so on. Okay. Um, I could also do some sort of mathematical operation where I have to do something a number of times. So let me just kind of, for sake of example, make one. Okay, and this is maybe bad. I consider it bad form to use a variable and a function that have the same name, even though sometimes you can get away with it. That's bad. Okay. So let me write a function that computes a number to a power. okay? And the way I want to think about this is, well, what could that power be? Some other number, right? So what should I return if that power is 0? Okay, so what's anything to the 0? 1. Well, we could save the philosophical argument as to what the heck 0 to the 0 is for later. Um, what's anything to the power of 1? Itself, so I'll just return the original number. And then, like, if I wanted to cube a number, what should I do? I multiply it by itself 3 times, okay? And so what I could do here is I could say for I in range, and then I need to think of what range to do here. Um, well, let's say we'll start with 0, and then, well, let's just try it, and we can always do this. We'll do answer equals, so actually let me come up here to the beginning, and let me define answer to be 1. And I'll do this, and then I'll return answer. Okay, let's test it out. And then how do I need to test it out? Well, let me get rid of this, and let me get rid of this input number business, and let's just let's print what did I call this? Power of well, let's take how about 2 to the power of 3? So what should print here? 8. All right, let's see if it does. It does. Okay. All right, let's do 2 to the power of 4. 16. Okay. So let's think about what's happening here. First off, I've got some checking, right? If the input is 0 for the power or is 1 for the power, I don't actually have to compute anything. I know what those values are, just spit them back, be done with it. And then otherwise, what I'm going to do is say, I defined this answer variable, and I just set its initial value to 1. That was important, because then what's going to happen if I multiply answer times the number? Well, I'm going to get just the number the first time, right? So let's say that we're doing our example where I put in 2 and 4, right? So 2 is the thing I'm exponentiating, 4 is the number of times. Okay, so when I come to this loop, 2 times 1 is 2. Okay, now I is 1. 2 times 2 is 4. Now I is 2. 2 times 4 is 8. And now num is 3. Or sorry, I is 3. And now 2 times 8 is 16, and we're finished, okay? So I've written here a loop that basically just continually multiplies by another factor of n, or the number, as many times as is necessary until I've run through it and I get my output, and hooray, that's it. Okay, does that kind of make sense? What potential issues do I still might have with this function? No, right. What do I do if I have either non-whole numbers or in fact negatives? Right. So what does a negative exponent mean? Yeah, you do 1 divided by that thing. Okay. And then the last thing is, what does a fractional exponent mean? Yeah, square roots and stuff like that. So something to the power of 1/2, for example, means a square root of a thing. But currently, do I have any protection against that being the case here? No. So if, for example, I tried to do 2 to the power of 1/2, it's going to croak because what kind of things can I use as a counting variable in a for loop? Well, I'm counting, right? So they have to be integers. So what does it mean to count from 0 to 0.5? But wait, what? Like it just doesn't make sense. Okay, so so obviously it's not going to work, and it even tells us the error here: float object cannot be interpreted as an integer, meaning 1/2 is a floating point number, but I should have an integer there for doing a loop. Okay, so right, so if we were writing this function to do just whole number powers, well, it's a perfectly fine function, but it doesn't work obviously if we um, have that, unless we added in more cases to handle that thing. And in fact, let me actually, if you guys will indulge me for a mathematical moment, how do you actually do um, x to the y and make sense out of this if x and y are not whole numbers?
Express y as a fraction.
Okay, but what about if you can't do that? So for example, could I ask you what is 2 to the, or well, let me just do 5. Could I ask you what 5 to the square root of 2 power is? I could, right? Is there any problem with that as a mathematical thing? No. All right. So you could type that into your calculator or Mathematica or Wolfram Alpha or something, and it'll spit out an answer. Okay, but how is it really doing that? Let me call the answer this. And then I'm going to deploy one of my favorite tricks. Yeah? I do the old E log trick. You fools, you fell for one of the classic blunders. No? Okay, so if I've got a function that can do exponentiation base E, and I've got a logarithm, and I can do multiplication, then I'm in business. Okay, so yeah, logarithms are your friends. So could we program something like this in? Sure, right? It just our function would be getting much more complicated. Okay, is that okay? All right. So, what I want to kind of finish with here, at least for today, and we'll look at an example of this on Wednesdays, but we'll look at it in a way that at first is going to have nothing whatsoever to do with functions, but it will, I promise. Okay, which is, um, could I have done the following? Let me change this line here. And I'm actually going to get rid of this indentation. And I'm going to do this. Okay, let's see if it works first, because if it doesn't work, then clearly I can't do it. Okay, what did I pass? Oh, that's why, because let me change this to, we were doing 2 to the power of 4, was it? Okay, do I get 16? Yeah, I did. Okay, so let's look at what I changed here. What have I done? Yeah, I've made the function reference itself, right? That's kind of weird. But if we think about this, what is 2 to the fourth? It's really 2 times 2 cubed. Well, what is 2 cubed? 2 times 2 squared. What is 2 squared? 2 times 2, right? And then if I just multiply all those things together, I get 16. Yes? So I've thought about this in a slightly different way mathematically, all right, which is to like think about it with a crap ton of parentheses or something. But what it gives us an example of a function whose definition refers to itself. Now, does that feel slimy? Oh, yeah? It feels real slimy? Why does it feel slimy?
Defining something based on itself doesn't really give a definition.
Well, it does. Okay. This is called, when we do this, recursion. Okay. And remember, how many of you guys stocked up on your favorite headache medicine over the weekend, like I warned you? You got the oxys ready to, yeah. Somebody's got like a fentanyl lab going in their dorm room or something, or uh, Breaking Bad. Um, okay, so a function that references itself is called recursive. Now, you can't just do this willy-nilly, okay? There are limits to how you do recursion, and in particular, it can't go on infinitely. If it does, then you're in a math class setting, but on a computer, it can't actually do that, okay? Yeah.
Like if you input a fixed number for pow,
Then it's going to croak. And in fact, that's the same error that I had here, right? Is that this recursion would go on forever. And because I never programmed in a case for what to do if the power was negative, okay? But if the power is a positive, so let's just, assume that everything works nicely, then asking what is 2 to the fourth is synonymous with saying what's 2 times 2 to the third. Well, what's 2 times 2? What's 2 to the third? 2 times 2 squared. What's 2 squared? 2 times 2 to the first. What's 2 to the first? Oh, we have a case for that, and we're no longer referencing the function itself, right? So the recursion eventually stops. Okay, so the way I like to think about recursion, there's a couple of ways. Um, is how many of you guys have been to an Outback Steakhouse in the not too distant past? Okay, what is the best thing to get in an Outback Steakhouse? The onion. Forget the steak. Actually, the steaks are pretty good, right? But what do you get? You get the appetizer, which is really like a meal for an entire week for one adult, right? The bloomin' onion, right? So it's that thing, right? And it's all battered and deep fried and delicious with the sauce that's even worse for you, and there's grease everywhere, and it's so tasty. Okay, but think about an onion. Okay, what happens if you peel a layer off of an onion? There's another slightly smaller onion contained within that thing, right? And if you peel off another layer, there's still another onion, okay? And it goes all the way, and eventually you hit the core of the onion, which is the part that, unless you're chopping it, you toss, right? Um, Recursion is kind of like that, okay? We're peeling layers of onions. Or maybe another way to think of this is how many of you guys have ever seen either seen or seen pictures of the Matryoshka dolls? Okay, so these are those Russian dolls where you open the doll up and what's inside? A slightly smaller doll that looks the same, and then you open that one up and what's inside of that? Okay, and it gets down to eventually there's some tiniest doll that's in the middle, right? It has to stop eventually, right? Again, recursion, we want to kind of think of it like that. Okay, so Wednesday, what we're going to do is I'm going to give you guys an exercise in recursive thinking that you may not think is going to be recursive at first. Yes, you got to think in cursive. You have to think with portals. Okay. And then Friday we'll kind of analyze this in a bit more detail, and then also bring it back to kind of computer territory. All right, let's quit. Well, I guess a minute early. So yeah, see ya.